So we finish with the Reynolds number. Remember, there are two equations. This one is the Reynolds number if we have P and T at the pressure of the pipe, and this one is P and T pressure is 40.7 and temperature is 60 degree Fahrenheit or 520 degree Rankine, and Z is 1. So if we have a different story in the pipe, we will have different number. Use this one. Okay, and remember that Q, the rate is in MSCFD, and gamma G is the specific gravity of gas with dimensionless, viscosity in centipoise, and the diameter is inches, because it already been divided by 12. So remember that divided by 12, the D in here is inches. So the D in here is inches, okay? Remember that the D is in inches. So this one, remember for the unit. It is important for the unit. I might end up deduct your grade, your score if you are on the exam, on the homework, if you don't put a unit on it. Continue with one phase. Remember from deriving the two-phase flow, you have three different type of friction, type of pressure drop. The first is friction, and the second is gravity, the third acceleration. And in this case, we don't put any as if the pressure is there is no pressure drop due to hydrostatic, so it's just horizontal and no acceleration, so it's a steady state condition. Okay. Why I put dPdL? Because of the direction. Remember on the derivation of a basic equation of fluid flow, you have the negative, and then we put a positive number, so become a positive. So if we put in the different way to write it down, it become this way. So the density depends on the pressure. Okay, friction not actually, velocity is not that much, so especially 2D, and we put the GC on it for the constant, gravity constant, and then a DL on here, and then we use dimension analysis. We have this long equation. So what we want is the density is in feet cube pound mass per feet cube. Pressure is in PSIA, because in here, if you see in here, is everything is in feet. So we have PSIA instead of PSF, pound force per square inch. And the friction is dimensionless. The velocity is feet cube a second cube. D is 1 feet. Remember feet in here. And the GC is pound. GC is a pound mass feet, pound force second square, and L in feet. So if we put everything in here, so we have this equation. Remember that on this density, when we talk about the Reynolds number for a gas, we have a density of this equation. So we have this equation of from the initial one. So this initial one become 1. Okay. And now we talk about the rate that we have. Usually measure the rate and everything is from the surface. Remember that? From the surface, not in the bottom. So, and not in the pipe. So usually the rate is after a separator, means that on the standard condition. And okay, so we want to define gas velocity in the pipe, not on the surface. But what we have actually is velocity from the surface. The data that we have is from the surface. So let's see that the V, we want to V in feet per second, V in SIA. So we have a condition base. Condition base is the standard condition, and the condition pressure and temperature PT, and from the ID gas pressure of in the pipe, V in the pipe, V on the PT, Z and RT, and then become NR become this way. So if we talk about P base, okay, V on the surface and Z base and etc. And then remember that NR become this one. So this NR the same as this NR. So we end up with having this equation. Okay, and then from this equation you see, and then let's see. Since we have a Q, a V in here, and V volume in here, if we put divided by day in here, divided by day in here, and we end up with having this equation. So instead of V, we have a Q of P and T out and in the tubing, and Q in the what you call it, in the surface. So P, Q of inside the pipe is equal to this number. So the VQPT divided by A, so become this long equation. Okay, so Q, this is Q from separator on the surface, PB, base P, 14.7 probably, T of a pipe, Z of a pipe, P of a pipe, TB, base temperature of the surface, and ZB is equal to 1 because on the standard condition, and A is P over P d square is over A on this one. Okay, and we want a feet per second. So if we plug everything in here, so feet per second, 4,144, everything is fine except just P and D square. So we end up with having V equal to this equation. If we put Q in MSCFD, D in inches, okay, D square become 144. Remember that we want inches, and we end up with having this equation. Okay, and then we plug this equation 2 to equation 1, remember here, and we end up with having this long equation, and we put what you call it, unit on it. So inches, everything in inches, L is in mile usually. So we end up with having this long equation. This is because of the inches, and this one because of the equation above. It's already been there. 1 feet is equal to 5,280 miles. Okay. So this one is mile, this one from the equation above, and this one because of the phi. And this one will already mentioned in above. And then we put instead of this form, so we decided to multiply by p and put an integral on it, p1 over p2. Okay, so instead of p in the bottom, we have p up, there is no p. Multiply by p. Okay, so let's see, where is p here? Oh, there is a little bit mistake here. 14.77. Where is it? 14.77. Okay, it should be no. Let's see. Okay. So if you multiply by p square instead of p square, so this one has a p square, disappear after the p square, and this one only one p become a p here. Understand that? Okay. And if we continue to solve this integral, we have this number, we have this equation. Solve for this one, we have the equation. Okay. Remember, this one is p square, 1 over p square. So this to be multiplied by p square. So if we solve everything to q square and solve everything, okay, q square is somewhere around here, this one, q square, and then we have this equation, or finally we have q this equation. This is the final q equation. Okay, this is called a Darcy equation for pipe flow in a pipe. Q, remember, NMSFD, and T base and P base and T base, and T base and P base, T and T in degree Rankine, P base, P1 and P2 PSI, T in inches, gas gradient is dimensionless, Z dimensionless, F dimensionless, and L in a mile. So if we assuming that the TB and PB is 520 degree Rankine and 40.7 psia, so this is the equation for Darcy equation. So this is the general equation, and this is if you have a so PB and TB is a standard condition. So this equation actually is a trial and error equation. We will continue with trial and error later on.